In today's class, we will discuss about the deadband circuits for inverters and their effect of dead time in voltage, output voltage waveform, and also we'll see how to compensate that loss or voltage loss in case of dead time circuits. So deadband circuits. So first thing is, so why exactly we need these dead time circuits, right? So you're aware that this switch and this switch, so S1 and S4 are complementary to each other. That means when S1 is on, so this must be off. So if this simultaneously turn on, when these two switches are simultaneously on, what will happen is that the source is short circuited like this. So it will cause enormous current and it will cause the failure of these two devices, and as well as if the source is not supporting or the source is not protected, and the source may be failed. So to avoid that at any cost, so these two switches must be turned on with some time delay. So why actually this dead time will happen? So normally when you are giving the firing pulses, right? So this pulse is normally like this. For the negative signal, so this pulse will be something like this, right? So this is 0 to 1 transition. So this is 1 to 0 transition. So this is S1 and S4. So this is ideal. But practically what's happening is, so here the switches are, or the switching is not instantaneous. So it is having, for example, turn on time. So it is having two terms. One is the delay time and the rise time. Similarly, for turn off, you have two things. One is the fall time and delay time and fall time. So that composed of two terms. So if this is the ideal transition, so but in practically, it will be something like this, right? It consists of two things. So one of the rise thing, one of the delay time and the rise time. So this entire thing is turn on time. So this is usually in the order of 10 to the power of -7 to 10 to the power of -9. It is usually in the order of 10 to the power of -7 to 10 to the power of -9. So depending on the switches. So usually for MOSFETs, so this delay time is or the turn on time is very small when compared to this IGBTs. Similarly, this is turn off time. So when this device is turned on, so it is having some time delay. So this is known as T off, or the turn off time, right? So during this, when this device is turning on and the device is turning off. So during these intervals, right? So during these intervals or during this time period, so what will happen? So this device may be completely turned on and this device may be completely turned on. So what will happen if you cause the inverter to or the one phase leg to short circuit? So what we have to do is, so we have to intentionally delay the pulses such that, for example, this is the actual thing. So we need to give some time delay, something like this. So this is the time delay. So instead of turning on at the instant, so we need to wait for 1 or 2 microseconds, and we have to make sure that the device is completely turned off, right? The device is completely turned off, and we are turning on the, or we are turning on again. So this time period usually 1 microsecond to 2 microsecond delay. In case of MOSFETs, so this value may be 0.1 microsecond to even less than 0.5 or 0.5 microsecond or 0.2 microsecond, something like that. So next thing is, so how to provide, or so first thing is, so we'll see so how to draw the waveforms for ideal voltage case. So let us assume that we have inverter here. So this is the pole voltage. So this is Vs by 2 here, and this is Vs by 2. This is the pole voltage point 0. So assume that, so this one is a triangle carrier. We have triangle carrier comparison, right? So assume this is triangle carrier. So in this carrier, this modulating signal is varying like this. One modulating signal, so is varying like this. So here you have this triangle carrier, and this is your modulating signal. So I assumed that, so during this period, so this is constant, right? So during this period, this variation is constant for my simplicity. Clear? So let us draw the waveforms. Right. So let us draw the waveforms for this particular case. So let's draw it for S1. Right. So let's draw it for S1. So how it will be? So when this modulating signal is greater than that, right? So that means this signal is 0 here, and you have positive here, or the pulse is on here, right? So this is the signal. So how exactly this S4 will be? So how the S4 will be? Complementary of this, right? So this will be like this. Agree? So let us assume that this is the pole voltage Vs0. So pole voltage varying from plus Vs by 2 to minus Vs by 2. So right, if you divide this into three parts, this is 1 here, 2 here, and this 3 here. Right. So during mode 1, so what is the pole voltage?
Minus Vs by 2.
Minus Vs by 2. So this is minus Vs by 2. And here mode 2,
Vs by 2.
plus Vs by 2. And again, so it is minus Vs by 2. So these are the ideal transitions, right? So these are the ideal transitions. So let us assume that, so this current is positive, right? So this current is positive. So which device is actually conducting here? So this is D1 and this is D4. So which device is actually conducting here? If the current is positive. Which device is in conduction?
D4, sir.
So here the voltage is negative, right? But the current is positive. So that means the current will be flow like this, right? So what is the device it is in conduction?
D4, sir.
D4, right? Agree? So here, which device is in conduction? Current is positive, voltage is positive. So which device is in conduction?
S1, sir.
S1.
S1. And here, in mode 3,
Again D4.
again D4 in
D4.
conduction, right? So this is for positive current. So in case of negative current, so which one will conduct here? In case the current direction is something like this. So what will conduct now?
S4.
S4.
S4 will conduct. And here,
D1.
D1.
so D1 will conduct here, right? And here, again,
S4.
S4. Clear? So keep this aside, right? So here these are the ideal. So we assumed that the turn on time of the switch or the turn off time of the switch is almost zero, or practically this is instantaneous. The rising edge and the falling edges are instantaneous, right? So now, so this is actual pulses S1A. So this is actual. So this is ideal. So how exactly this actual pulse is? So this is whenever you have some turn on instant is there, right? This is rising edges, right? This point it's trying to turn on. So what we have to do is we need to wait for some time. So we need to wait for some time. So this is like this, right? It's supposed to turn on here, right? It's supposed to rise here. Instead of that, so we need to wait for some time. We need to wait for some time. Actually, I'm drawing, right? We need to wait for some time. So this will be the ideal transition. So instead of that, so we are waiting for some time and the pulse is now on, right? But during the falling edge, so this is the falling edge, right? So here, so this is as it is. Clear? Similarly, S4 actual, so as we already discussed that, so this is the falling edge. So falling edge as it is, and so here continues to conduct or continues to be zero. And here, so this is the rising edge. So rising edge is delayed by some time period. So this time period, this is TD, and this is also TD. This TD is the time delay time. Clear? This TD is the delay time. Understood? So what is our assumption is that, so this T on or T off of the switch is negligible when compared to this TD. So that means this TD is much greater than, or much less than, much greater than these values. That's why, so instead of drawing like this, so we have drawn a sharp rising and sharp falling edges. So these are the actual transitions. Clear? So what exactly we did that, so whenever we have them rising edge, so that rising edge is delayed by some duration or some time delay, maybe 1 or 2 microseconds delay, and the falling edges are as it is, and the falling edges are as it is, right? So now, so this is the output voltage, right? So now the question is, so how this output voltage changes, so that we need to identify. So this is the original pulses. So when you have original pulses or when you have ideal pulses, so this is the one. But so we have some delayed pulses. So we have some delayed pulses. So with this delayed pulses, so how this output voltage is affecting, so that we need to identify. It's clear? Right. So before that, so first what we have to do is, so how to obtain a specific time delay. So how to obtain a specific delay, so that we need to, so how to implement that, so that we need to identify. So these PWM schemes are usually developed either in software based or the hardware based. So in case of software based, you can always use some delay circuits, so that will delay your waveform or delay your pulses. For example, you have, this is the original pulse. If we give some delay counters or something delay signals, so that means, so we have some delayed pulse, it's supposed to be transit here. So instead of that, so it will be like this. So this period is TD. So instead of that, so when you're doing with analog circuits, so what we have to do is, so this entire setup, so you're aware that this RC circuit, so that will gives you some time delay. So let us assume that it will be like this. For example, your voltage will be like this, right? So this is a transition to 5 volts. So if you connect a RC circuit, so what will happen instead of that? So this RC circuit, it will rise like this, right? Okay. So let's draw the waveforms. So this is waveform is delayed. So that means you have original signal like this. So let us assume this is the original signal, right? And this is the delayed signal. So this is delayed signal with RC. So this is how it will be, right? Agree? So this is the original pulse. So that means this is 1 here and this is 2. Right? So, but what we have to do is we need to provide the time delay only for the rising edge, not for the falling edge. So, but when you're delaying this, so what will happen? So this rising edge is delayed and this falling edge is also delayed, right? So that means instead of that, so we have some time delay instead of this is the original waveform, right? So when you apply only this RC circuit, so what is the resultant is, so this waveform is delayed, something like this, and this waveform is just delayed. So that means this waveform is shifted by some time period delay, right? So but instead of that, so we need to, so instead of that, so we need to remove the delay, or we stop that, so we need to stop here exactly at falling edge. Right. So what we have to do is, so if we connect an AND gate here, if we connect an AND gate here, so what exactly you will get here? So these portions, right, whatever this portion is there, so that will be cropped. So when the AND gate is right, so when the AND gate is on, or when AND gate is 1, so when this is 1, this is 1, so then only you can get 1, right? So that means you will get a waveform something like this. So this is output of AND gate. Right. So now the thing is, so why these two NOT gates are connected side by side? Right. So there is no use of this one. For example, this is 1, so this will be 0 and this will be 1. So two NOT gates are connected means, so it is not altering the pulse. So whatever here, so the same value here, right? But the thing is that, so here, because of this RC circuits, we have some exponential rise or exponential delay is there, right? So what exactly this will do is, instead of that, so this kind of waveforms, so it will produce a sharp rising edge and sharp falling edge. So it means it will raise the edges. Instead of that, if you connect these two NOT gates, so that means, so it will produce a sharp rising edge pulses. So like this. So whenever some time delay is there, so instead of this kind of waveforms, if you want to produce a sharp edges, so usually we'll connect two buffer circuits or two NOT gates side by side or in series. So that is what we followed in electronic circuits, right? So here, so this particular setup, whatever the time delay is there, right? So that is dictated by this time constant RC. So for particular case, so this will provide 1 microsecond time delay. So here R is 1 kilo ohm and this is 0.001 microfarad. So this is for 1 microsecond time delay. So instead of that, you need required 2 microsecond time delay. What we have to do is instead of this 1k ohm, so you need to replace with 2k ohm resistor. Clear? So that gives you 2 microsecond time delay. So why exactly these two NOT gates are required? For example, they have 5 volts is there, right? So but the ICs are start working from so 3.3 volts. So if you have NOT gate here, so it will wait until 3.3 volts reached. So once it reached, so this starts working, right? So after that, so this is also start working. So once that reach this 3.3 volt limit, so that's why, so this time constant, whatever here is there, right? So that means exactly same period only. So we, that means a sharp rising edge can be provided. So you can see here, so similarly we need to produce, this is for upper device and this is for lower device. Similarly, you have to produce the time delay for lower circuits. So this is also processed in the same one. This is S4. So we have experimental waveforms. So here, this is the first pulse. So this is for S1, right? So this is S4. So these are delayed, right? So here, so this is the, so this one, right? This one is the actual transition. So this one is the actual transition. So here, this is the delayed. So this is whatever this gap is there, right? So this is 1 microsecond. So each one is 10 microseconds, right? So this is the off of that one. So that's why you have 1 microsecond time delay is there. Similarly, this is the actual transition and this one is the delayed transition. Okay? So this is how we will provide the time delays by using hardware circuits or by using analog circuits. The thing we need to remember is especially this time constant of this RC, so that will dictate the delay time, right? And another thing is connecting these two NOT gates side by side, back to back, so that gives you a sharp rising edge pulses. You can either connect these NOT gates or you can connect some delay blocks. So this NOT gate, so will not extend the waveform. That means it will clip or it will remove these portions. Clear? So you have any questions? You have any questions?
Sir,
Yes.
those NOT gates will have
Hmm.
some propagation delays.
No, no, there is no delay here.
Propagation.
Hmm?
Propagation delay.
No, no, it will not provide any delay. This whatever the delay it is giving, the same thing is also giving, right?
Okay, okay.
Right. So this is how experimentally we provide the delay. In case of what we have software approaches, like if you're using some software related things to generate the firing pulses, so in that case no need to worry. So in that you can use some delay blocks, so that will provide the required time delay, right? So come to our actual discussion. So this is the ideal voltage, right? So this is the ideal voltage. So now we will see so how this ideal voltage is modified, so with the introduction of this time delays. So we have two scenarios. So when the current is positive, right, or the current is negative. So we'll start from the, if the current is positive, let us assume that, so IA is positive. So that is this direction. So when the currents are positive, so this D4 is conducting, S1 and D4 are conducting, right? Okay. So when the current is positive, if you assume that the positive current, so from here to here, right? So from here to here, so this pulse is I and this pulse is no. That means you have negative pole voltage, right? So which device is actually conducting here? So which device is actually conducting? For positive current,
D4.
which device is actually conducting?
D4.
D4, right? Agree?
Yes, sir.
So D4 is actually conducting, right? So now, so from here to here, so there is no change in the output. So now, so during delay time, so that means during this time, so which switches are actually conducting? So during delay time, so which switches are actually conducting? So if you see that, it's a S1 is low, right? So S4 is also low. So no device is in conduction, right? Agree?
Yes, sir.
So during this first delay time, so no device is conducting. So during this period of time, so no device is in conduction. So what will happen? What will happen? So to make the current continuous, so what we have to do, what supposed to there is, so this conduction is repeating. That means the diode is start conducting. Agree? The diode is still in conduction, right? So now once this delay time is over, so once this delay time is over, so now during this period, so this is on and this is off. So now what is the voltage? What is the voltage?
Positive.
Vs by 2.
Vs by 2, right? That means this is Vs by 2. Yeah. So here D4 is conducting. So here which device is in conduction?
S1.
S1, right? So now, so during this period, again, so S1 is turned off. S1 is turned off. S4 is supposed to turn on, but it is delayed. So now what will happen? So how the current is maintained? So how the current is maintained?
Or conduct.
So here this S1 is off, right? So here the basic thing is as and when you remove the firing pulse, the switch will be completely off, right? So somehow the current must be route. So how the current will flow?
Through D4, sir.
Again,
D4.
so the current is
D4.
transferred from S1 to D4, right? So that means this is the point again. So this D4 is in conduction. It's clear? It's clear. So that means, so here this is as it is. There is no change here. No change here. But here, right? So here this is supposed to start here, but here it is starting here, right? So how much voltage is lost here? How much voltage is lost? So this area, right? Agree? Agree?
Yes, sir.
Right. So this is lost area or we are gaining here. It's supposed to be here, right? But it is here. Some of the voltage is lost, right? So how it will be? If this is the axis, so how it will be? It will be something like this, right? So what is this value? What is this value? This peak value.
Vs by 2.
Yes, by 2.
Why Vs by 2?
Vs, sir. Okay,
So this
peak
is
to peak
Vs,
Vs.
right? So
Peak to
here,
peak Vs.
so this is we are subtracting the V ideal minus V actual. Okay. So this is VS0 ideal minus VS0 actual. So it will be Vs only, right? Agree? Agree? We're subtracting the ideal minus the actual pole voltage. This is clear? So first thing, so what you have to understand that if the right, if the diode is an already conduction, right? If the diode is in already conduction, if the incoming device, right? If the incoming device is a transistor, so in that case, if your delay time is there, so the diode will continues to conduct. So here the diode is continues to conduct, right? So in this case, so both switches are off. So this switch is off, this switch is off. So what will happen? So the switches S1 is off. So that means the current is transferring from S1 to D4. Right. So here the transfer of current is delayed from D4 to S1. So that is delayed from D4 to S1. So that is delayed. Right. But from S1 to D4, so that is instantaneous. So this is D4 to S1, right? So that is delayed here. So whereas this one is instantaneous. So what we have to understand from diode to IGBT, the transfer is delayed, right? Diode to IGBT, the transfer is delayed. So but whereas from IGBT to diode, so that is instantaneous. It's clear? So any questions here? So you have any questions? Okay, in that case, we'll move to the next case. So this is for positive current case. So these are the ideal ones. So these are the ideal transitions in the pole voltage. So now we assume that so IA is negative. Right? So here ideally it's what is supposed to conduct here in this case. So from here to here,
S4.
what's supposed to conduct?
S4.
Yes, yes,
Four.
S4, right?
Yes.
Agree? So this is S4, right? So now during this period, so both are turned off, right? So both switches are turned off. So now which one is supposed to conduct?
D1.
D1.
Right. So that means S4 is off. So that means this is off, right? So the switch S4 is off. So what it's supposed to do is the incoming device is D4. We already discussed that. So diode to switch is delayed, but the switch to diode is instantaneous. So this is switch to diode. The switch is off, right? So this is instantaneous. So it will be continue like this. So which device is conducting here? D1, agree? So this period also D1 is in conduction during this delay time. So now this is over. So now what will happen? So what will happen now? So during this delay time,
D1 will continue.
so D1 will continue to conduction up to
With
S4
delay.
rises, right? So up to this point, so D1 is continuous to conduct, agree? So at this instant, so this S4 is on, so that means, so this is like this. Right. So it's supposed to stop here, but so this is delayed, right? So now, so voltage gain is happening or voltage, so this is the voltage gain, right? Agree? Agree?
Yes, sir.
So this will be the voltage gain. So how to represent this is we are shown as loss rate. This is the voltage loss here, right? So this is voltage loss. So how to represent this voltage gain? So we may represent so like this, right? So this width is TD. So what is the magnitude here? So what is its magnitude?
Yes.
Plus Vs. Agree? Its magnitude is plus Vs. So if you summarize the things, right? If you summarize the things, so if you have IA, so if you have IA, so that is positive, right? So there will be a voltage lost in output voltage. So how much voltage it is lost? How much volt second? So this is Vs into TD. So this much of volt second, so that is lost. So if this IA is negative, voltage gain. So this gain is Vs into TD. So this is happening for every carrier cycle. So this is happening for every carrier cycle, right? So this is happening for every carrier cycle. So that means, so it will be something like this, right? So this is for one carrier cycle. So here this value is plus Vs and this is minus Vs. So what is the shape of current? So current is, so this is for positive current. So we are lost, right? So that means, so it will be positive here and it will be negative here. Agree? So this is IA. Is clear? So here
Yes.
it is each one is TD time. If you have something like this, if it is continuous like this, right? So during this period, so it will be on. So remember, this is voltage and this is current. It's clear? So this is the error, or this is the voltage lost here, and this is the voltage gain here. So if we make an average, right? If we make an average this one, so these pulses, right? So all are having the width TD and magnitude Vs, and it is happening for every carrier cycle. It is happening for every carrier cycle. So therefore, we can average this one, right? So we can average this one something like this. Right? So we can average this one something like this. So what is this value? So what is this value? What is this average value here? So what is the average value of this one? So that is TD into Vs. So that is happening for every carrier cycle, right? So that is TC is the carrier cycle. Agree? Agree? So that means, so this value is TD into Vs by TC. So where this TC is the carrier cycle. So in every one carrier cycle, so we have this delayed pulse or the delayed error. Right. So now, so this is the voltage lost. So this will be the voltage lost overall, and this will be the voltage gain. So if you superimpose on the modulating signal, so it will be like this. So we have this original modulating signal, or this is the ideal one, and we have the current here, or the inverter current, right? So this one is the modulating signal, and this is the inverter current here. So based on the current, right? So this is the positive current here. So therefore you have negative pulses, or error is negative here. And for negative current, so you have positive errors, or the positive, or the voltage gains here. So you can average this one into something like this, and this average is something like this, right? So here, so due to this one, right? So this is last here, right? So this is supposed to be here, but right, the actual one is slightly reduced. So we are superimposing, so this original one, so that means this waveform and this square wave, this one. So 1 minus 2 we are doing, say we are getting, so this actual waveform. So this one. Clear? So this is how the fundamental voltage, so that's varying. So you can see here, this is the one, what is the ideal one, right? But due to the voltage lost here, so there is some reduction here. So there is some reduction in the fundamental here, and similarly there is a reduction in the fundamental, or there is some modification in the fundamental here. Clear? Right. So here now tell me, so the overall voltage is reduced or increased? The overall output voltage is modified, right? So overall output voltage is modified. So depending on the inverter current. So when the inverter current is positive, the output voltage is reduced this much, right? So here also if you notice that the output voltage is reduced here. So only during the transitions at this case only, so there is actual increase in the output voltage. So if you notice that, so here you have increased, right? So here also reduced. So this is reduced here. So this is reduced here. So that means overall, so with some delay circuits, so the output voltage reduced. Output voltage is reduced. And the second thing is that, so it induces, so we have the square wave, right? So this is square wave. If you decompose the square wave into harmonic components, we have third, fundamental, third, fifth, seventh, and so on. So even though the triplet harmonics are so not or if cancelled in the line voltages, right? But this lower order, fifth and seventh order harmonics, so will adjust. So if you decompose this waveform into Fourier components, we have this high frequency, low frequency component, fundamental, fifth, seventh, ninth, and so on. But this third or ninth order harmonics or the triplet harmonics, so that will be present in the pole voltage, but it will not present in the line voltage. So that means the line voltage will consist of the fifth, seventh, 11th, 13th, small amounts of this lower order harmonics. And moreover, so this is switching pulses. For example, these are harmonics that are present at carrier frequency, or in other words, MF times the carrier frequency, 2MF times the carrier frequency, and so on. So it emerges lower order harmonics. So delay circuits cause lower order harmonics. So lower order harmonics. So these two are the drawbacks, right? So these two are the drawbacks with the delay circuits. So how much? So what is the value of this one? So what is the error? This one will be TD into Vs by Tc, where Tc is the triangle carrier period. Right. So this value is significant, right? So when you require a high performance inverter applications, so this value is significant. So what we have to do is, so we need to compensate this one. So we need to compensate this one. So how to compensate this one is, so based on the magnitude or based on the polarity of the current, right? So based on the polarity of the current, so this error is varying, right? So based on the polarity of current, so this voltage gain or the loss is varying. So therefore what we have to do is, we need to identify the current polarity by using a current sensor, right? And we need to add the, so whatever this error is there, right? For example, so here 230 volts is there for some instant. So you calculate the error voltage is some 5 volts. So error voltage, so this value are calculated as 5 volts. And for at particular some instant, so that voltage is 230 volts. Right. So actually what's happening is, instead of that, if we assume that the current is positive, right? So that means the voltage is reduced to 225 volts. So what we have to do is, whatever this extra voltage 5 volts is there, right? So that we have to compensate this one. So we need to add this voltage so that, so we need to add this voltage so that you can get, so this 230 volts again. So that means error voltage, whatever the voltage that lost, so that we need to compensate by adding to the modulating signal. So how to do that? So this is the one. So we have circuit here. So this is the dead time circuit. So this is providing some time delay. So we have the upper switch here, lower switch here, and this is the inverter current. So here we are measuring the inverter current. we are measuring the inverter current, right? So based on, this is the original modulating signal, original, right? So based on the inverter polarity, so we are adding or subtracting some small error. So this is the error voltage. So for positive current, the current compensation is positive, the voltage compensation is positive. So for the negative voltage, so it will be negative, or the negative current, so it will be negative. So based on that, so whatever the error or whatever the voltage that lost, so that is compensated. So this is the error voltage, so that is added. So again, we have this PWM control, and this is the dead time circuit, so that is giving the pulses. So that means this is the error voltage. So this is the voltage. So what is the compensator? This is the one original. This is the voltage lost or voltage gain. The inverse of this one. So that means, so this will be added here to the modulating signal, and this will be added to the modulating signal. So now this waveform is traces the ideal one. So now this waveform traces the ideal modulating signal. So this is how we will provide the time delay. Right. So we also studied the disadvantage of this delay circuits. So and also we studied so how to compensate so this error or in the deadband circuits, error causing by errors, voltage lost caused by the deadband circuits. So you have any questions? You have any questions?